Welcome to our tutorial on using instancing for performance optimization in Java. In this video, we'll explore what instancing is, why it's critical for high-performance applications, and how to implement it in your projects. Are you ready to unlock new levels of efficiency? Let's dive in. First off, let's clarify what instancing means in our context. Instancing refers to efficiently creating multiple copies of an object in memory without the overhead of duplicating the entire object. This technique is especially useful in graphics programming and game development, where many sprites or models share the same attributes. Now, why is instancing important? When rendering a scene with numerous objects, each object typically has its own set of properties and data stored in memory, leading to performance bottlenecks. By using instancing, we can reduce memory usage, improve cache efficiency, and ultimately enhance rendering performance. Let's visualize this by looking at a standard rendering approach versus instancing. In our first example, we're going to create a simple scene where we render multiple cube instances without instancing. We'll examine the performance hit of not using this optimization technique. Here, we're simply looping through 1,000 cubes and rendering them one by one. Once you run this code, you'll notice that performance can drop significantly as we increase the count. Now, let's see how we can use instancing to address this issue. Before we dive into code, it's essential to establish a basic structure for our instanced rendering. We'll create an instance of our cube with transformation attributes and handle batch rendering. This way, we can send multiple cube instances to the GPU in one call, which significantly boosts performance. In this instance cubes class, we created a cube object and an array of transformation matrices. The create transformation matrix method translates each cube to its corresponding position. Then, in the render instance method, we render each cube, but with a single call for each transformed instance. Now, let's optimize the rendering part further. Instead of rendering each cube, we can send all transformation data to the GPU in a single draw call. This is where understanding your graphics API becomes pivotal, as underlying implementations vary significantly between libraries. This new approach utilizes a batching technique, where we prepare all data that's needed for rendering ahead of time. This preparation can involve uploading all vertex data to the GPU in a single send operation, thereby minimizing the context switch overhead between CPU and GPU. Performance profiling is crucial in understanding the gains we make with instancing. Make sure to test your application with and without instancing enabled to see the differences in frame rates and overall performance. By toggling between these two approaches, you can effectively measure the impact of instancing on your application's performance. Keep in mind that optimal values can vary based on hardware, so profiling in real-world scenarios is critical. Let's summarize what we've covered so far. We learned the definition and importance of instancing. We examined a standard rendering method and identified its performance bottlenecks. We implemented instanced rendering techniques that optimize performance by batching and creating transformation matrices for multiple instances. So, what's next? Going further, you can extend this idea not just for cubes, but for any object you want to render in your application. Consider using instancing for trees in a forest, enemies in a game, or other repeated elements within your scene. Another area for expansion is applying instanced rendering with different shaders per instance. This can allow for variations, such as different colors or textures, while still maintaining the performance advantage of instancing. Additionally, there are libraries like OpenGL and DirectX that native support instancing. We may provide methods that help you easily transition your objects to leverage instancing more effectively. For instance, let's define our generic create instance method, which can be tailored to any graphics library. As an exercise, I recommend implementing instanced rendering in a mini project of your own. For example, create a simple game scene with multiple enemies or obstacles and optimize it using instancing. Evaluate your performance optimizations through profiling. Before we wrap up, let's review some debugging techniques. While implementing instancing, issues may arise. Understanding how to visualize instances and check if they are rendering correctly can save you hours of frustration. Using these debugging techniques, you can effectively verify the correct placement and attributes of your instances. Don't forget to take advantage of graphical debugging tools provided in your graphics libraries. Finally, let's summarize what we did today. We covered instancing and its importance for performance optimization, learned various techniques to implement instance rendering, explored testing and debugging strategies, and envisioned future applications of instancing in diverse scenarios. Remember, optimization is an ongoing journey, so keep researching and implementing new techniques in your projects. Thank you for joining me today. If you found this video helpful, please like, subscribe, and hit the notification bell to receive updates on our latest tutorials. Let me know in the comments section about your thoughts on instancing or any topics you'd like me to cover next. Happy coding, and I'll see you in the next tutorial.